Hi everyone, I'm John Boprosky and welcome to my webinar on a free receiver CTLE IBIS-AMI model generator that can be used in any channel simulator. Please type any questions into chat as I proceed with this webinar. I will have a questions and answer session at the end of the webinar. You can also email me with your comments and questions at johnb@serdesdesign.com. Why is this webinar needed? High-speed digital integrated circuits and serializer deserializer systems have their physical layer modeled and simulated in a channel simulator. Channel simulators are designed to use IBIS-AMI models that are based on the IBIS specification. Many commercial IBIS-AMI model generation tools cost tens of thousands of dollars to lease or to own. Today, the SerDes channel simulation technology has matured so that it is available for free using cloud-based tools at SerDesDesign.com. Included with the SerDesDesign.com tools are options to generate IBIS-AMI models from circuit data collected from SPICE circuit simulations or from hardware measurements. This webinar is to let you know about the process I have used for many years to generate IBIS-AMI models from any channel simulator, and it's available to you for free. What is SerDesDesign.com? I created SerDesDesign.com to enable me to create and deliver IBIS-AMI models to 40+ high-speed digital integrated circuit companies over the past 10+ years. Over that time, I learned many processes that practically guarantee a better, more efficient, and automatic IBIS-AMI model building process using free tools. I learned how to create high-quality, low-cost IBIS-AMI models while avoiding the standard approach using high-cost tools. Along the way, I learned that expensive tools kill all chances you have of achieving low-cost, high-quality IBIS-AMI models. My tools are based on free tools, Microsoft Visual Studio, CMake, web browsers, HTML, and so forth. I learned that creating an IBIS-AMI model should be the last thing you concern yourself with when it comes to creating IBIS-AMI models. Focus on collecting the correct circuit simulation or measurement data, and use automation. My tools rely on automation to generate models from measured and simulated data. I learned how to escape the costly commercial tool trap that keeps most persons stuck in a permanent high-cost model creation situation. Many of my tools are available for free on the web at SerDesDesign.com with options to download and install local copies on your Windows or Linux machines. I am here to share my learnings over the past 10+ years and introduce you to the same IBIS-AMI model generation capability I have used to create and deliver high-quality, low-cost IBIS-AMI models. What this webinar will show you. This webinar first gives an overview of modeling SerDes systems in a channel simulator. Then I introduce the process I use to create IBIS-AMI models for receiver CTLEs. Define the CTLE with poles and zeros, or with spectrums, or with peaking values, or with circuit waveforms. Include the ability to de-embed the IBIS portion from the data collected to derive the AMI portion, and generate an independent standalone IBIS-AMI model from the data. Finally, I show you how you can get a copy of my free receiver CTLE model generator for use with any channel simulator. Modeling the SerDes system in a channel simulator. Channel simulators are based on the IBIS Open Forum standard, currently at revision 7.2. This figure shows a typical SerDes system block diagram to be simulated using a channel simulator. This block diagram is generic for any channel simulator, but each tool has its specific way to represent this block diagram. The constituent parts of this SerDes system include the following: the transmit IBIS-AMI model. The AMI portion typically contains a transmit equalizer, often in the form of a feed-forward equalizer, and an IBIS portion that provides the differential output to the channel. There's a transmit package, the channel itself, and a receive package. These pieces represent the differential channel. Each part is optional and may be represented using S parameter files. And there's the receive IBIS-AMI model. The IBIS portion has a differential input from the channel. The AMI portion typically contains a receiver CTLE, CDR, and DFE. A key channel simulator property to keep in mind is that it considers the entire analog content, the green area in this figure, the total channel, between the TX-AMI portion and the Rx-AMI portion as linear and time invariant. As an LTI system, the entire differential analog section in the SerDes system is accurately represented by its single-ended impulse response. This key concept enables a channel simulator to achieve its fast simulation speeds. The creating IBIS-AMI models from circuit data. IBIS-AMI model generation from behavioral data was built into the SerDesDesign.com channel simulator from the beginning. I've used this process over the past 10 plus years, providing custom IBIS-AMI models to over 40 plus companies based on the circuit data that are provided to me. In today's webinar, I provide instructions on generating received CTLE models from circuit data. The modeling is collected typically from a SPICE circuit simulator. Modeling other types of transmit and receive SerDes is discussed in other SerDesDesign.com webinar. To start, let's talk about the typical SerDes custom test points. This figure shows typical test points for a SerDes system. For the current discussion, test points 0, 4, and 5 are used for data collection. NRZ data streams are used for modeling, though the Rx IBIS-AMI models may support PAM4 as well. TP0 is for the NRZ waveform. The data collected at TP4 is the Rx SerDes differential input. TP5 is the Rx CTLE output. The data collected includes the IBIS differential input buffer characteristics, the CTLE behavioral characteristics, and output time domain waveforms. Here's the top level Rx CTLE IBIS-AMI model. There's an IBIS input portion and an AMI output portion. The IBIS portion is for the circuit input and defines the buffer input impedance interfacing the differential SerDes channel. The AMI portion contains the algorithmic code that performs the equalization and does not have any impedance characteristics. The model discussed here is defined as linear and time invariant. It can be used in the channel simulator statistical mode and in the time domain mode. Its characteristic is represented by its impulse response, which is convolved with the channel impulse response. There are two basic Rx IBIS modeling approaches. The typical Rx IBIS buffer model is composed of an RLC circuit with additional voltage current tables or per differential output pin, input pin, as shown in this figure. The IBIS buffer model is quite limiting and does not do a good job modeling the actual Rx circuit input impedance. However, per the IBIS spec 7.0 and beyond, the IBIS portion can now be modeled using 4-port S parameters. This approach is a full fidelity approach that will accurately represent the Rx circuit input impedance facing the differential channel. My experience has shown that most Rx SerDes circuit designers cannot easily separate out the S4P data from the output buffer of the Rx circuit. Fortunately, the Rx IBIS S4P data can be obtained from S2P data. I've used this approach for my customers for many years. All that is required is to measure the Rx input differential reflection coefficient. This is called the SDD11 characteristic. To convert the S2P data into S4P data that is usable as an IBIS model, set up the S parameter schematic with this S2P file as shown in this lower left schematic. The differential input impedance characteristics will be the same as the original S2P data when the output S4P is loaded with an infinite load resistance. Be sure to use a linear frequency sweep with the same start, stop, and step frequencies as the S2P data. We're now ready to discuss the Rx AMI modeling options. There are two types of modeling approaches that are provided. One approach models the Rx circuit CTLE behaviorally with poles and zeros. Any number of CTLE states are allowed. The CTLE states can be defined with a list of poles and zeros or with peaking characteristics defined in the frequency domain. Another approach to the model the Rx circuit is as a black box. Without a priori knowledge of the CTLE characteristics, the Rx circuit input to output time domain waveform or frequency domain characteristics can be measured, and the Rx circuit input loaded into match 0 Hertz load resistance. The CTLE behavioral modeling approach is discussed here. It's defined with a list of poles and zeros. Use any number of poles and zeros, including complex poles and zeros. One can alternatively define the poles and zeros by simply defining the peaking response in the frequency domain. Define the frequency and a list of dB peaking values. The order of the peaking can be specified. A larger order results in steeper frequency domain characteristics. The normalization can be specified at the peaking frequency or at 0 Hertz. This figure shows 9 state CTLEs with all peaking at 20 gigahertz. When the CTLE is specified, it can be defined as inclusive of the IBIS characteristic or exclusive of it. When it includes the IBIS portion, then the model automatically de-embeds the IBIS portion from the behavioral model to obtain the characteristics for use in the AMI portion. The CTLE can also be modeled as a black box. For this modeling approach, the Rx circuit is characterized over a full or partial set of CTLE states. The Rx circuit characterization processes from the differential input to the CTLE output. It uses a PRVS waveform pattern that has a portion of the pattern with a consecutive set of M0s and N1s such that M and N are large enough to allow for state settling. So waveforms or spectrums are collected with a matching 0 Hertz source resistance. This approach requires de-embedding the IBIS characteristics from each of the waveforms. This de-embedding is performed automatically in the model during simulation for the specific symbol, rate, and samples per symbol used. Let's talk about de-embedding the IBIS characteristic to obtain the AMI model. In this figure, H of S is the received circuit differential input to CTLE output transfer function and is defined by the Rx CTLE time domain waveforms or frequency domain spectrums or even the pole zeros characteristics. H of 1 of S is the IBIS portion. H2 of S is the AMI portion that must be derived. Since H of S is equal to H1 of S times H2 of S, then H2 of S is the ratio of H of S divided by H1 of S. These transformations are carried out in the AMI model to obtain the equivalent time domain representation of H2 of S for use in the simulations. Here's an example using the Keysight ADS channel simulator. In this ADS schematic, the Rx AMI model is set up using the SerDesDesign.com Rx SerDes CTLE with step response model. This is a behavioral model that uses Rx circuit waveform data obtained from SPICE simulations. This model will be used to generate an independent IBIS-AMI model. For this example, SerDes channel is defined with S parameters. This plot shows the SDD21 channel characteristics. It has 24 dB lost at Nyquist, which is 12.5 gigahertz. Thanks to Silicon Creations LLC for use of their ADS copy. Removing ADS High-frequency aliasing is a process built into the SerDesDesign.com process. In this example, the S parameters go out to 40 gigahertz, the blue curve in the upper left graph. The ADS channel impulse response in the frequency domain, the red curve in the upper left graph, accurately tracks the S parameters to 40 gigahertz. After 40 gigahertz, the ADS channel impulse response has high-frequency aliasing. SerDesDesign.com anti-aliasing, the purple curve in the lower right graph, accurately tracks the ADS response and removes aliasing beyond the S parameter maximum frequency of 40 gigahertz. This is done with no added delay, as shown in the upper right graph in the time domain. Modeling the example Rx IBIS. In this example, the Rx circuit input impedance was measured as S2P data. That data showed that the Rx circuit input resistance at 0 hertz is 53.96 ohms per pin. That S2P data was converted to S4P data using the approach discussed earlier. Modeling the example Rx CTLE. Any number of CTLE states are supported. In this example, it's based on defining the CTLE with 32 states, each defined with time domain step response waveforms. Typical slow and fast corner cases are supported. Each corner has its specific IBIS S4P file, and the IBIS buffer characteristic will be de-embedded to obtain the AMI model. For modeling the CTLE, collect the Rx circuit output waveforms and matching 0 hertz source resistance for all CTLE states using NRZ data. The waveforms shown here are from the typical corner case. Modeling the example Rx CTLE. During the simulation, the Rx AMI model converts the Rx circuit waveform data into an equivalent AMI portion by de-embedding the IBIS characteristics from the circuit data. The Rx AMI model automatically selects the CTLE state configuration for optimal channel equalization, and optional AGC is also available in the model. The CTLE configuration is used to obtain the Rx impulse response and the impulse response for the combined total transmit, channel, and Rx. The model automatically de-embeds the IBIS from the waveform data. The upper plot shows the Rx model output impulse response, which includes the Rx IBIS characteristics for a specific CTLE state. The bottom right plot shows the Rx CTLE response, which is an exact match to the original reference waveform data. The Rx circuit waveform data represents the cascade of the Rx IBIS portion and the Rx AMI portion. During channel simulation, the Rx IBIS model is automatically de-embedded from the Rx circuit waveform data to derive the Rx AMI portion. So, when ready to generate the IBIS-AMI model, set the parameter enable gen IBIS-AMI to 1. It then generates an independent standalone IBIS-AMI model, and along with the defined names that you define for generating the model. The messages shown below are displayed in the channel simulator message panel. The IBIS-AMI model files are generated. The DLL for Windows or SO file for Linux file contains the encoded waveform data for all 3 corner cases. Now it's time to use the generated IBIS-AMI model. The generated model in this example is named Rx CTLE with step response and has 4 generated files: the IBIS file, the AMI file, the DLL for Windows or SO for Linux, and a configuration file that contains all the modeling data encoded for use. The generated IBIS-AMI model can be used in any channel simulator. Only the parameters exported during IBIS-AMI model generation are used. The user can define the names for those exported parameters. Generate as many new IBIS-AMI models as you want for free. Alternatives for model generation. Circuit data used in this example was the Rx differential input impedance and the Rx CTLE input-output waveform step responses. Alternative modeling approaches can include the use of spectrums, the use of pole zero data, the use of frequency domain peaking characteristics. For all alternatives, corner cases are supported, and IBIS de-embedding is supported, and 4 files are generated: the IBIS file, AMI file, the DLL or SO, and the configuration file that contains the encrypted encoded circuit data. The generated IBIS-AMI models can be used in any channel simulator. So, summary. This webinar introduced you to the free Rx CTLE IBIS-AMI model generator. It is one of the tools I've used over the past 10 years, providing IBIS-AMI models to 40+ SerDes customers. The Rx SerDes IBIS-AMI model generator enables you to define the CTLE with poles and zeros, or with spectrums, or with peaking values, or with circuit waveforms. It supports de-embedding the IBIS portion from the circuit data to obtain the AMI portion, and it supports generating a portable Rx IBIS-AMI model that can be used in any channel simulator. Its free time-based license can be renewed for free. The tool and its generated IBIS-AMI models rely on the same free time-based license. The original license issued is for 1 month. The license can be renewed for free on a monthly basis as needed. A 12-month license is also available for a fee. The removal of the license restrictions for the generated IBIS-AMI model so that the IBIS-AMI model can be used on any Windows Linux computer is also available for a fee. The source code with a build project can also be obtained. The build project can be used on Windows and Linux, and it's available for a fee. And this build project can be used as a starting point for your further customization. So for further consideration, SerDesDesign.com has many other free IBIS-AMI model generation tools. See our store at this website. Besides this CTLE model generator, there's a transmit FFE model generator, an Rx model generator that includes CTLE, CDR, and DFE. There's a repeater model generator that includes back channel training with the transmit and receive generators. And there's a electrical repeater that also includes back channel training, which includes not only the transmit and receive portions, but also an optical VCSEL fiber PIN and TIA generator. This webinar has been on SerDesDesign.com free IBIS-AMI model generation tools. Each IBIS-AMI model generation tool comes with a time-based license. Use the tool free for 1 month. Renew the free tool license as many times as you like for free. See ordering instructions for the available free tools at this website, posted below, and see the link below. Well, this completes the presentation content of this webinar. I'll end the recording of the webinar and spend time with you to address your comments and questions. Remember, you can also email me with your comments and questions at johnb@serdesdesign.com. So, bye for now.